Here's an equation that looks fairly harmless at first, but I think it's hiding something interesting. We need to find the values of y in y squared minus 2, all squared, equals y plus 2. Before we do anything, just study the equation for a moment. What stands out? The left side is the square of an entire expression, while the right side is only linear. That difference is our first clue. We have a choice to make. We could take square roots, but that would introduce the square root of y plus 2, making the equation even more complicated. Instead, let's expand the square. That transforms everything into a polynomial, and polynomials are much easier to analyze. We'll use the identity that says a minus b, all squared, is equal to a squared minus 2ab plus b squared. When you compare the expressions, y squared represents a, while 2 represents b. Applying it here gives y squared raised to the second power minus 2 times y squared times 2 plus 2 squared. Now simplify each term. Y squared raised to the second power becomes y to the fourth. 2 times y squared times 2 becomes 4y squared. And 2 squared becomes 4. So the left side is now y to the fourth minus 4y squared plus 4. Substitute that back into the equation, and we get y to the fourth minus 4y squared plus 4 equals y plus 2. To solve the polynomial equation, it's usually best to collect every term on one side. Subtract y, then subtract 2. That gives us y to the fourth minus 4y squared minus y plus 2 equals 0. Now the equation is in a form we can investigate. Whenever I see a polynomial with integer coefficients, I immediately wonder whether it has a rational root. If it does, factoring becomes much easier. The Rational Root Theorem tells us that any rational root must divide the constant term. Since the constant term is 2, our only possible candidates are positive 1, negative 1, positive 2, and negative 2. Let's test the first candidate. If y equals positive 1, we get 1 to the fourth minus 4 times 1 squared minus 1 plus 2. Simplifying gives 1 minus 4 minus 1 plus 2 equals negative 2. That's not 0, so positive 1 isn't a root. Let's try negative 1 instead. Substituting gives negative 1 to the fourth minus 4 times negative 1 fourth minus 4 times negative 1 squared minus negative 1 plus 2. Simplifying, we obtain 1 minus 4 plus 1 plus 2 equals 0. That's our first breakthrough. Since negative 1 is a root, the factor theorem tells us that y plus 1 must be a factor of the polynomial. Now divide the polynomial by y plus 1. After dividing, we're left with y cubed minus y squared minus 3y plus 2. So we can now rewrite the polynomial as y plus 1 multiplied by y cubed minus y squared minus 3y plus 2. We've reduced a fourth-degree equation to a cubic. That's a big step forward. But we're not done yet. Now the question becomes, can this cubic reveal another rational root? Let's find out. We'll test positive 2. Substituting gives 2 cubed minus 2 squared minus 3 times 2 plus 2. Simplifying, we get 8 minus 4 minus 6 plus 2 equals 0. Another breakthrough. That means positive 2 is also a root, so y minus 2 must be another factor. After dividing the cubic by y minus 2, we're left with y squared plus y minus 1. So we can now rewrite the polynomial as y plus 1 multiplied by y minus 2 multiplied by y squared plus y minus 1 equals 0. The first two factors immediately give us y equals -1 and y equals 2. Now all that's left is the quadratic. Y squared plus y minus 1 equals 0. This quadratic doesn't factor nicely over the integers, so the quadratic formula is the most natural choice. Applying it, we get y equals -1 plus or minus the square root of 1 squared minus 4 times 1 times -1, all divided by 2 times 1. Now simplify the expression inside the square root. 1 minus -4 becomes 5. So that leaves us with two more solutions. Y equals -1 plus or minus the square root of 5, all divided by 2. Let's gather every solution we've found. They are -1, 2, -1 plus the square root of 5, all divided by 2, and -1 minus the square root of 5, all divided by 2. Remember, mathematics isn't about memorizing tricks. It's about discovering patterns. Keep exploring, keep asking why, and I'll see you in the next lesson.